So in the previous video we saw two different ways of calculating traction on some arbitrary plane inside a body at a point. Okay, we saw two different pictures, which one of them was simply a matrix operation and other was the coordinate transformation. Okay, and we used the fact that the components inside a 3x3 stress tensor are nothing but the component of traction on the basis plane in the basis directions in the second method. Okay, so now let us do more things with it. Okay, so we know how to find traction at any oriented plane at a point. We just saw two methods for that. Okay, and the traction vector is usually oriented in some way on this plane. It is not always normal. It could be normal, but it's not always normal. It could be oriented in any random direction. Okay, so and we saw that we can use these two methods. Okay, this one was the coordinate transformation, in which you can directly read the traction values from the coordinate from the matrix itself. Another one was using sigma n is equals to t, or the Cauchy stress theorem. So now consider this random plane at a point P inside a body. This is a normal unit vector for this plane, and this is the traction, direction of the traction on the surface at a point. Okay, so now if you take the projection of this traction along the normal, okay, so you take the projection this side, and also you take the projection on the plane, okay, on this plane. So you get two components. This is sigma n perpendicular and a sigma n parallel. Okay, this sigma n perpendicular is actually the direction of the normal vector, which is perpendicular to the plane in which you are making the observations, and sigma n parallel is actually along the surface. And these two components of the traction vector, okay, are called the normal component or the shear component. Note that they are not stress. Okay, we sometimes call them stresses, but basically they are tractions. Okay, whatever you are deal with, you mathematically whatever you do, you are only dealing with tractions. You can't deal with stresses directly, although you can do it in the tensor calculus, that we are not going to discuss it here. But in this video we never directly manipulated stresses apart from doing those transformations using Q. Okay, so if you take the projection of your traction on any plane of some random orientation depicted by this normal unit vector n, so these projections along and perpendicular to the surface of interest are called the normal stress and the shear stress components. Okay, shear traction components actually. Yeah, so how do we calculate them? Let us try to calculate them and why they are important. Okay, so definitely you know why they are important, right? If you know a bit of structural strength of material, because we know tensile stresses, which are now you know that they are tensile tractions, and shear stresses, which now you know are stress shear tractions. Okay, now how to evaluate them? It's very simple. You just take the projection, dot product of Tn with respect to n. Since this is a unit vector, you'll get directly you'll get this vector, this Tn parallel to n. I think we have messed up the representation, the perpendicular and parallel, so just keep in mind this. This is the normal component, this is a shear component. Okay, so here we mean that this is parallel to n and this perpendicular is perpendicular to n. Okay, in the previous figure we call them perpendicular to the plane, so I think we should use a consistent representation. Let us make this parallel and make this perpendicular. Okay, fine. So this parallel means parallel to the normal vector, and perpendicular means that's perpendicular to the normal unit vector. So how to calculate the normal component? Very quickly we'll see that. So there's a projection here and the direction. Okay, this is a vector, so that's why we need direction. So this is the direction. Okay, unit vector direction, and this term will give a scalar value. Dot product will always give the scalar value. This will give you the length of this vector and another direction. So completely we'll get the t parallel n. Similarly, we can calculate the shear component by simply subtracting from this vector. Okay, so t perpendicular n is nothing but t n minus this, which is nothing but this t parallel n, and we can represent this as these two normal components, the shear components, in this form. Okay, so sigma n represent this result of this dot product, n is the normal unit vector, and tau n here, this is the shear, we call them shear stress component. This is the length of this green vector, and this is calculated from this. It's nothing but taking magnitude of this, and m is nothing but normalizing this vector by dividing it by its magnitude, so we get a unit vector out of it. So that's very simple representation of calculation of this normal and tangential or shear stress components of the traction. Okay, nothing complicated in this slide. Yeah, so this is the m direction that we talked about, which is given by this vector. This is also unit vector m vector, and sigma n and tau n are nothing but the length of this green and the pink vectors. Now we are going to discuss some specific planes and specific direction. We talked about infinite directions, okay, but there are few directions or few planes that are interesting. Okay, they are in some way special. So why are they special? We'll see after the discussion why are they special. And for to start, let us start something like this. So we know that we change the coordinate system or rotate the stress cube, the component of the stress tensor changes. That we have seen, because coordinate system is chosen by us. So as you change it, the representation changes. So there might exist a particular coordinate system where the component of the stress tensor will maximum, minimum, or some special values. Okay, these components will tweak, right? Will change somehow, and it's possible you'll observe some kind of pattern. Okay, something will go to maximum, minimum, and it's interesting to see how these things changes as you transform or change, or transformation of the stress cube is simply rotating it in different orientations using this q times sigma times q transpose, that kind of operation that we saw in the previous video. You can rotate the cube. I'll also try to make a simple MATLAB implementation of these things. I've already done it for a 2D example. I'll try to do it for the 3D and upload it along with this series of videos. Okay, so let us take an example of first order tensor first, that is the vectors. Okay, so this is the vector v, and as we rotate these bases e1 and e2 is in such a way, okay, that one of the bases aligns with v, then we get one of the elements 0. Okay, one of the component is 0 and another one attains the full possible maximum value. Another way of doing it is rotating it anti-clockwise or clockwise, and again another, in this basis the first component is 0 and another one attains the maximum value. So in this way there are special kind of orientations at which you get these special values like 0, one of them has become 0. This actually simplifies the calculations if you are doing it, and also you understand, you gain much more insight, okay, into into your problem, because this, for example, in stresses, these components are nothing but tractions. So if the traction value is getting maximum at some point, that is actually of interest to you, because that's a critical, that plane is a critical plane in which failure could occur, right? So these values are important from the practical point of view also. Okay, so these special directions are called principal directions, and the corresponding values of the component that we get are called the principal values. Okay, they are usually the non-zero values. For example, in this example, the v is the principal value, okay, and there are two principal directions, right? In this principal direction we have the principal value, first principal value is v, second is also v. Okay, so we are actually not getting much from this, right? So That's what we are talking we are stating here, that for the vectors this principal direction doesn't give us much insight, because we already know that if you simply align your basis with along the vector, you will get the maximum and the minimum value, because there will be no component in the other direction, right? So we are not getting much, because since these stress tensors are actually superior quantity and we are not actually understanding them very well, we can't imagine them very well, so we could use these kind of things, like somehow let's see how this component changes as you rotate your stress cube, and can you gain some more insights from them. Okay, so let us define them, the principal direction and the principal values, like this, as an eigenvalue problem. Okay, so if there exists a parameter lambda such that sigma operating on n is equal to lambda time n. What does this statement means? That you are inputting a vector, unit vector, normal unit vector n, you are operating it with sigma. What you are getting out is a scaled version of sigma. Okay, so this matrix is not able to rotate. Okay, so whatever the traction is, it is actually parallel to the normal unit vector, like pressure. Okay, so on these directions you'll only get what? You won't get the cross terms, right? So you expect that you will only get a diagonal term, right? So each term, right? So traction, the direction of the traction is similar to the direction of the n. That's what this statement says. Lambda is a scaling factor, okay, that will actually give you the value on the diagonal of the sigma matrix. Okay, so if this kind of n exists, okay, then this n is called the principal direction or the eigenvector, and this parameter lambda is called the eigenvalue. Okay, and this is a basically eigenvalue problem. Now what we want to find out is n, or if you could correctly find out what a n is, you get a sigma, and you then represent the sigma in that coordinate system. Okay, this given by n. Okay, as you will see, the output of this problem will be 3 perpendicular unit vectors, say n1, n2, n3, and you represent your sigma. Currently, for example, it's represented in some basis e, and you represent it in this basis n. Okay, where all the basis vectors are nothing but the principal directions. In that case, what you will get all diagonal elements, right? Okay, and you already know the meaning of this expression, right? The traction on this principal direction is parallel to the normal unit vector. That's what this statement says. Now you can take this lambda this side, and I is an identity matrix for this system. This is a homogeneous system of equations. For a non-trivial solution, this determinant of this sigma minus lambda should be 0. This just using basic linear algebra here, and we just from solving this sigma minus lambda I will get a characteristic equation, which is a cubic equation in lambda, right? Because we have 3 rows, and lambda will be multiplied thrice, because lambda is in each of the rows. So as you calculate the det, it will be a cubic term like this, where I1, I2, I3 are called the invariants of the tensor. This equation is called the characteristic equation. Okay, and I1, I2, I3 are the invariants. Okay, and why are they called invariants? Because these invariants doesn't change with the coordinate transformation. We saw that the components itself changes the values, okay, as you change the coordinate system, but these quantities, these scalar values like I1, I2, I3 are like a constant thing for a stress tensor. Okay, it doesn't matter which orientation it is, this value will be constant, which are actually some combination of the components itself. Okay, so there is a relation between the components which is always maintained no matter what the transformation is. Okay, so for example, these invariants are the trace of sigma. If you from the basic linear algebra, matrix algebra, you know that trace of a matrix is always the same no matter how you transform it, right? And the I2, which is nothing but this expression, the sum of 3 determinants. Okay, and I3 is nothing but determinant of this matrix. These are the 3 invariants. We are not going to discuss much of this. We are just interested in understanding the principal direction and the principal value and what insights we can get from these directions. Okay, so when we solve these, okay, we'll get three values of lambda 1, lambda 2 and lambda 3 and corresponding eigenvectors n1, n2 and n3. Why are we getting 3? Because in this equation, if we put lambda 1, okay, and then we try to solve, we'll get 1n. For lambda 2 and lambda 3, you'll get 3 n's. Okay, and if this lambda 1, lambda 2, lambda 3 are unique, right? So in that case, you'll get n1, n2, n3 will be orthogonal. We are not discussing the non-unique cases. Just you can look up into any book if you want to, but for this purpose, just for introducing principal values and principal direction, we just consider that we have a very good stress tensor in which these eigenvalues lambda 1, lambda 2, lambda 3 are unique. Okay, and all of them are different, right? So in this case, we get three orthogonal vectors n1, n2, n3, and for example, if your matrix currently is represented in this basis e1, e2, e3, and this is a traction on this surface. Now again, let us try to represent this a component in this form. That's what actually different way of seeing what we have seen in a single formula. So sigma ej, okay, it will give you traction on plane ej, right? For example, on plane e2, if you act on sigma, if you try to operate sigma on ej, you will get traction on the surface. For example, say on e3, you get this t, and then you take a dot product in direction ei. For example, e1, you get sigma 1, 3. So that's what this statement is telling. Okay. Now, suppose that we have chosen the coordinate system such that the eigenvectors n1, n2, n3 are now basis functions. This is basis. These are basis vectors. Okay. These are basic vectors, not functions. So in that case, what you will see? Let us see. So sigma n is equal to lambda n, that was the eigenvalue problem. Okay. Now n1, n2, n3 are our basis, similar to e1, e2, e3 now. Okay. We have calculated n1, n2, n3 from the eigenvalue problem as an output of the eigenvalue problem. Okay. So we write for sigma like this. This is actually three equations. Sigma n1 is equal to lambda 1 n1. Sigma n2 is equal to lambda 2 n2. Sigma n3 is equal to lambda 3 n3. There are three equations. Okay. Which are obtained from solving this. Okay, we didn't know n. Okay, after solving this characteristic equation, calculating lambda, putting it back into this, we calculated these three orthogonal vector n1, n2, n3. Right now, sigma ij from this expression we can write, because now this is our basis vectors. We can write ni dot sigma nj. Okay, and now from this expression we write nj. Okay, nj, this sigma nj is equal to lambda j nj, right? We take lambda j because it's a scalar, and ni dot nj, since these are orthogonal set of vectors, we can replace it by a conical delta, which actually nothing but saying that the dot product if with itself is 1 and with another one is 0, like this delta ij is equals to 1 if I is equals to j, if dot product is with itself, if it's with another one like n1 dot n2, it will be 0. So that's how sigma ij is represented. Okay, so what does it tell? For all non-diagonal terms, this value is 0, right? For diagonal terms, the values are lambda 1, lambda 2 and lambda 3. Okay, that's what we from this expression we tried to figure out just by this expression what this expression means. N's are those directions in which if you operate sigma, the traction will always be parallel to n, because it's lambda times right n. So this is what the traction is right now if you operate it. So both are parallel. Okay, just scaled version of n. This is your traction. So that's what after the analysis we finally come into what those directions are, and we finally see that if you express this stress tensor, which was earlier in some basis e1, e2, e3, into a new basis whose basis vectors are n1, n2 and n3, then you get a special form of the Cauchy stress tensor in which all non-diagonal terms are 0 and the diagonal terms are nothing but the eigenvalues that you calculate from solving the eigenvalue problem. Okay, now so that's what we did the previous and that's what we concluded, that the non-diagonal terms are 0 and diagonal terms are this, and so we get this stress tensor of this form. Okay, and if you assume that lambda 1, lambda 2 and lambda 3 are arranged in this order, okay, you name it something like this, and we already assume that they are unique, and in this case, and also we just for simplicity, because since we have been using sigma throughout, so let us just replace lambda by sigma, just a representation change, and these sigma 1, sigma 2, sigma 3, which were lambda 1, 2, lambda 2 and lambda 3, are called the principal stress components, right? Principal stress components. So they are not stress, they should be called as principal traction components, but that's the lingo that that's used in literature, that's why we are using principal stress components, but actually they are principal traction components, right? So that's what we see, that's where we were. Okay, we calculated this special direction n1, n2, n3. Now we transform this, we rotate this cube, stress cube, to align with n1, n2 and n3, and what we see is that this cross terms, okay, this n1, 1, 3, n2, 3 vanishes. Okay, only term that remaining are sigma 1, sigma 3, sigma 1 and sigma 2. So we saw that these are nothing but the projection of the traction on along the normal direction. What we call them stress, the normal components. Okay, and along the surface we call them shear components. So in this configuration, in this coordinate system, there are no shear components, right? There are only normal components. Okay, and you'll see that these are some of the maximum values that these diagonal elements could attain. Okay, that actually puts a upper bound on what these values, these diagonal elements could achieve. Okay, that's what we are saying here, that they provide a lower and upper bound on what these diagonal elements could take. Okay, so this actually closes our discussion on the stresses, what the stresses are, and in the next video probably we'll discuss how things changes using a demonstration in MATLAB, so in which you can play with the orientation, and you can see that how these values changes. Wow, what happens on the principal direction, does these values actually become 0? So you'll get to interactively you can play in that application. I'll also upload the link so you can download and play with it. Okay, so let us summarize everything now. So we started with tractions, we introduced tractions. Okay, we wanted to study what's happening at a point. We introduced tractions from the Cauchy's postulate, and then we moved towards introducing what linear transformation is. From where did linear transformation come? Because we saw that this traction were dependent on the orientation of the plane in which you are making the observation, and Cauchy said that there is a relationship between the normal vector and the traction on the plane of which this n is a normal unit vector, and this relationship is linear transformation. So we saw in a video what linear transformations are, and we saw that the function, okay, that relates n to the t can be represented as a matrix operation. Okay, then we introduced what Cauchy stresses are. Okay, right, we first introduced what a stress is, and we concluded that the function, okay, the transformer function which we were discussing and the stresses are actually the same thing. Okay, we discussed the Cauchy stress theorem. There we introduced what Cauchy stresses are. Okay, then we talked about representation of physical properties. Okay, we saw that scalars and vectors and second order tensors. The second order tensors, we call them some superior way of representing superior properties. We talked about double directions. Okay, what does this mean? Okay, in context of stresses, the double direction is nothing but direction of plane combined with the direction in which you are taking the component of the traction. Okay, and then we moved on to study of the tensors. Okay, and we saw several examples like what happens in the inertia tensor, and understanding of the various components of the tensor, what does it mean. We saw that in the next videos, and we saw that the components of the tensor as represented in a specific coordinate system is a 3x3 matrix is nothing but the component of the traction in the basis plane in the basis direction. Okay, now again, and we saw the stress cube to represent the tensors, especially the Cauchy stress tensor. We represented it in a stress cube where we use simultaneously we were seeing the impact of changing the orientation on the three planes. Okay, what is happening on the three planes, and the components of the Cauchy stress tensor can be directly plotted on the stress cube. Okay, then we moved on to study the coordinate transformation of the stress tensor and see how this component changes as we change the basis, and then we moved on to find a special basis function. Then we actually calculate the shear and normal tractions, okay, which were component of traction on a plane along the normal and along and along the surface on which you are making the observations. Then we finally did in this video the principal stresses and direction, which are some special direction in which only diagonal terms are non-zero, rest terms are zeros, and the values of the diagonal terms are called principal values. And we also saw that on these planes the shear component of the traction is zero, only normal component exists. Okay, so that's by this let us finish this theoretical part of this series, and I hope you got some insight into what stresses are. And in the next video we'll see a small demo of how things change using MATLAB's app builder. So thank you for your time, and please subscribe if you like this content. Yeah, that's it. Thank you.